have another candle, and just to prove to you that yes, they do turn black after the wick has been burned, we'll go ahead and light this candle. Light. Very stubborn. Okay, so here we have a candle burning, and when I blow it out, you do see that the wick turns black. So, we know that from your previous life experience that wicks that turn black. What?
Is that real? Can I eat this one?
Did I just like sprout another eye or something? You're all looking at me weird.
Can I eat this one?
That wasn't
Tell you what, I'll come around so you can make some observations and inferences about my candle.
Are they that good?
I don't know,
You can touch it, you just can't taste it.
that's not a candle.
It's like a candle.
It had a wick and it turned black after I lit it.
Put a wick in there and whatever it was.
Whoa.
Candle.
That's not, that's a banana. That's a banana.
It crunches. That's gross.
You heard that about
It's a cucumber. Take a couple of minutes, make some more observations after I've walked around and see if you can infer how I did this.
I guess she
ate the wick.
Yeah, you ate the wick.
Discuss in your groups observations and inferences. See if you can infer how I did this. You need to look at the candle again. It had a wick and it burned, and the wick turned black after it was burned. So it's a candle.
Paper turns black when you burn it, like golden on paper. Paper turns black when you burn it. So it could be like,
That's what I want you to discuss in your groups. How could I have done this trick?
You could eat another one, like another piece of it.
Does it feel like frozen
how much do
banana?
you think?
Does it smell like frozen banana?
A white candle. In Florida.
How did I do it?
Can I break this one and see what it looks like on the phone? It's probably cheese. No, but I did kind of like cheese, but I did it when I was flying. My dad told me to do it.
You can touch it.
I'm working them triceps, biceps, man. I'm getting my girls figured. Oh, let's go. All right, here we go. Y'all ready?
Ready? Charge! Whoa!
My mom. Okay. My mom.
Friday when we were starting the activity. They're trying to decide what wavelength of light they want to look at. So here are your options. Number one, Dr. Moon says we should look at a line in the visible spectrum. Dr. Moon's attitude is that's what we can see with our eyes, so there's no point in looking at anything else that we can't actually see. Dr. Luna says we should look at a line in the infrared. Infrared wavelengths are longer, so if you have a big area of gas and dust, those infrared wavelengths will be able to get through to it. Statement 3. Dr. Mond says we should look at a line in the ultraviolet. It doesn't have as much energy as visible or infrared, And that's a good thing, because too much energy would be dangerous and we don't want to get hurt. So take a minute and discuss in your groups, who do you agree with? Dr. Moon in visible light, Dr. Luna in infrared, or Dr. Mond in ultraviolet? Go ahead and talk and discuss. Why do you say Dr. Luna?
Yeah, and ultraviolet is just a little bit too high up on the scale. It's not like it's going to really hurt it.
Why Dr. Mond?
Infrared, you can see more.
It's less dangerous. Okay? And what do we have here?
Dr. Luna.
Why Dr. Luna?
Because infrared can pass through the gas and you can see the full object.
Okay. Who we got? Infrared. Why do you go with Dr. Luna?
Because ultraviolet is too high up on the scale and then too low on the scale.
Okay.
Oh, the red.
And what's your vote? Dr. Moon, Dr. Luna, or Dr. Mond? Why Dr. Mond? Okay. Trying to look, see if we get the gas and stuff. Okay, we have a nice kind of variance with Dr. Moon, Dr. Luna, and Dr. Mond here. So, to help you understand where these numbers are coming from, in your notebook, I want you to set up these data tables. So I'll turn to the next clean page. Is long, yeah, red wire, red, black.
And then
No, take the wire. Yeah, plug it in. I think that's supposed to be in the top one. Is this one the top one? Input. And then...
that sounds like a game show, so to be.
Now, play around with that.
Got it.
Okay, that. Okay, now play. Okay, here's your remote control.
It's a computer.
What do you do with it?
Okay, now have your setup turned on. Point your remote control at it. Okay, with remote controls, what type of energy do you think comes out of a remote control?
Microwave.
Not radio? Infrared. Infrared is where we're looking at. So what happens, you have an infrared LED light emitting diode here at the end. It's sending out that infrared signal, and that can be picked up on the photocell, just like visible light, just like ultraviolet light. It doesn't matter what kind of light it is, that photocell is going to be able to pick that up. When it comes to astronomy, you take the concept over. If you look at something only in visible light, you are missing a lot of the picture. So what I'm going to do next is show you a picture of constellation Orion, and this was taken in visible light. Using the grid that is already set up on the paper, pick one area that you would want to look at. Point your telescope towards it. Do you like A1, A2, A3? Maybe B1 is better.
I like C3.
Maybe B2. And look at B3. What about C1?
Yeah, but we're just looking for
What about C2? C3 might have something interesting.
I don't remember the brighter lights. See, this might be like hugely bright.
So like, I'd say B2 for those 3 to 4. Yeah.
Actually, I'm gonna go for the B3.
I'll just hit that blue giant.
Okay, so you like B3, you agree? I think you like different areas. Take a picture of Orion in the infrared.
Go.
Look at your picture and decide, do you still stick with the same area?
No, not at all.
Yes.
Or is there now an area that looks a little more interesting?
I said B3.
Because it's red.
I know, that's why I said that. Yeah, I guess.
Well, it's red though.
I mean, here, this like this, and then this.
What periods do those fit into? They seem to be kind of hanging out there in its own space. When you look at the periodic table, let's take a look at periods 6 and 7. So we're down here, we're looking at cesium. Cesium has atomic number 55. Barium has atomic number 56. Lanthanum 57. Hafnium 72. Time out. What happened to 58 and 71?
They're not there.
You're right down here at the bottom.
Oh.
Look at period 7. Francium 87, radium 88, actinium 89, rutherfordium 104. It looks like we're still missing some elements. Those go down here at the bottom. Question ready?
Yeah, I think they're not there. I think that's at the bottom.
Very good question. What I want you to do is take your main part of the periodic table. See that large, heavy black line? Cut it right there.
Tear it off?
Yeah.
You tear it off?
Just cut it.
Cut it. Cut it right off.
Shut up, dude.
I'm trying to help you.
Cut it right there. Spread it apart. Move those 2 bottom rows into place. This is the true shape of the periodic table. And to answer your question, can you fit this on 1 page?
Yes.
No.
You won't be able to on. So for your hypothesis, here's what I'd like you to think about in your lab notes. Hydrochloric acid. Since we've done everything with formulas now, you don't have to write out the entire name hydrochloric acid. You can just use the abbreviation formula, HCl. Just make sure you're capitalizing and lowercasing correctly. So hydrochloric acid, HCl, will react faster with, and then you make a choice. If you think it's going to be copper, or if you think it's going to be magnesium. Something that might influence your decision. When you look at the periodic table, talked about periodic trends. There's copper, and here's magnesium. So also think about their placement on the periodic table. How could that affect which one of these is going to react better with the hydrochloric acid? You're good. That looks like about a milliliter in each one.
So let's put copper.
Yep. Plop. Is it doing anything? Now try the other one.
So let's start with copper. Copper and trace.
Okay, so you see some bubbling. Yeah, it's bubbling. You can actually hear it. It's bubbling quite a bit. In fact, if you let that go for about a minute or so, feel the bottom of it in a minute or so. Yes.
Something's happening.
Very fizzy. Did the copper do anything?
Not yet.
Okay. How long has this one been fizzing?
Since we put it in.
Feel the bottom.
Wow. That's warm.
It's warm. This is also what we call an exothermic reaction. We're going to talk about that next week. So for your conclusion, my hypothesis was, and then fill in with true or false. Remember, it doesn't matter if your hypothesis was true or false. That's not part of your grade. It's how you back up what you're saying. So if your hypothesis was true, follow these steps. Restate your hypothesis. Reinforce what it is you're saying. My hypothesis was true. I thought this element would react more with hydrochloric acid, and it did. And then give me the data support. What did you see that backs up what it is you're saying? If your hypothesis was false, here is where you can correct your statement. I thought, my hypothesis was false. I thought this element would react faster, but it didn't. This other element did. So you can correct your hypothesis and make sure, again, you give me that data support. What backs up what you're saying. Chemical reaction, it is a gas being produced. This is pretty much the exact same thing that you just did. I've got hydrochloric acid, and I've got the more reactive of the two elements in here. But if we flip back to our reaction, it doesn't matter which one actually went faster, magnesium or copper, but please note they both produce hydrogen gas. I showed you a demonstration earlier this year when with vinegar and baking soda to show like the bubbling and everything, and that produced carbon dioxide gas. Well, when you see bubbling like this, how do you know what gas is being produced? You don't. You have to do some little test of some kind to see what gas is actually being produced. And that test is going to be based on whatever the chemical and physical properties are of your particular gas that you're after. Well, one of the big differences between carbon dioxide and hydrogen gas is that hydrogen is very flammable. Carbon dioxide is not. So if this produces hydrogen gas, what gas would be inside this bubble? Hydrogen gas. So what happens if I bring a lighted match next to these hydrogen bubbles? If it's really hydrogen, what's going to happen? Yep, it's hydrogen gas, all right. If it was carbon dioxide, it wouldn't do that. You wouldn't see that little pop in flow right there. Now, interesting thing about hydrogen gas. How does that, did I startle you? Yeah. Good. A little thing about hydrogen gas. If you've ever been to a football game, or you've even seen football games, on TV or whatever, you see they have blimps. And the thing with blimps started, they were real popular in the early 1900s. They were developed by the Germans. And the original gas used to get a blimp to float was hydrogen gas. Hydrogen gas works really well because it's less dense than air. And from the density stuff that we talked about yesterday, the less dense stuff floats, more dense stuff will sink to the bottom. So hydrogen gas is less dense than air. You fill a gigantic balloon with hydrogen gas, put a little thing on the bottom of it to carry people, and you've got a nice little early airship. Well, except the problem is that hydrogen is extremely flammable. So back on May 6, 1937, there was a passenger blimp by the name of the Hindenburg that had come over from Germany and was landing in New Jersey, and it had a small problem. It blew up. 37 people on board, all of them were killed. And the reason that it was such a disaster was because this entire thing was filled with hydrogen gas. You saw the big proof these little bit of bubbles right here have. Imagine a blimp full of hydrogen gas. Not any wonder that all those people died. So after this particular disaster, they switched to using helium. Now, you know that helium is still lighter than air. You've seen helium balloons, they float up. But when you look at where helium is on the periodic table, which is right here, what is another reason that helium is much better than hydrogen for filling a balloon. Matt? It's an inert gas, exactly. It's in that last column. It's an inert gas. It's a noble gas. So what is it not going to do? It's not going to react. It doesn't do a darn thing. So it's a lot safer than hydrogen. So the blimps that we use today, those are all filled up with helium gas so that it doesn't explode like what you saw right over here. Okay, we've got about 3 minutes to the bell rings. Go ahead and get your things together.